this is what the Tesla-shaped cavity, superconducting cavity, looks more or less at the end once the design is fulfilled. So in this case, we can see here in the center a 5-cell Tesla-shaped structure with the beam pipes, which are these cylinders here, and the waveguide dampers, which are these waveguides coming inside. So basically, the electron bunches come traveling through these beam pipes until they get to the cavity, and in principle, normally you use these cavities for acceleration, so they see the effect of the electric field induced inside the cavity and generated by the RF power that you put inside the cavity, and then they get accelerated until they get through and they continue traveling. So that means that by putting RF signal, RF power inside, we excite some resonant modes inside, and this would be, for example, the pi mode that we use for accelerating. This would be the fundamental mode. So as you can see here, an electron will come this way until it reaches the cavity, then he starts feeling, the electron starts feeling the electric field, which has, as you can see, a longitudinal component, and then it gets accelerated, and since this signal in the cavity is oscillating, this RF field, then it will continue seeing a constant field through, and then it will get acceleration until it reaches the end. So the thing is that these cavities, every cavity has not only one resonant frequency, it has many resonant frequencies. So that means that we will have high order modes, high order resonant frequencies that could disturb the behavior of our cavity. So in principle, we have many other different modes, like it could be this one, for example. This one appears at 1.7 gigahertz in this case, and it's a dipole mode. Dipole mode means, in this case, as you can see, the electric field component is no longer longitudinal but transverse. So when the electron comes in, if this mode is excited and it has enough affection on the electron bunches, it can disturb the beam. So it's something that we don't want, and we should get rid of it. So for that, we use these waveguide dampers I told you before. So for example, if we plot the absolute value of the field in colors, you can see that even when this mode is excited inside, we can get rid of it by extracting the power through the waveguides. So that's a whole design process that we have to do, and of course we have to do too many optimizations until we get the correct designs and the correct distance from these waveguides to the cell and the correct geometries. But to design all this stuff, we have to start from the basics, and that means that we have to start by designing the center cell. And for that, we usually start from simple approximation. So we start by designing just this cell, as I told you before, and we have to start from a 2D sketch like this. So this would be the geometry for a typical Tesla-shaped cavity that is used for this acceleration in this case, and we use the pi mode, as I said. So you have to tune this radius here, the radius of the equator, the radius of the iris, which is this window here, in order to get the precise electric and magnetic field values that you need to get your acceleration, but not getting too much that you could get into troubles afterwards. So by doing parametric analysis of these different geometries and doing electromagnetic simulations, we get the field profiles and we can analyze all that. So for example, here you can see the electric field which is generated inside this structure for the pi mode. And here you can see, as explained before, that you have this longitudinal electric field which would cause acceleration, and that we have, for example, high field values on this area here. So you have to be very careful when you design this, so the values of your electric field in this area are not that much that you could get into troubles afterwards. Of course, you can plot as well the magnetic field, and here, as you can see, and as you know, the electric and magnetic field are always linked. So in this case, since we have magnetic field going through the structure, doing a loop through the structure, this induces electric field in the other direction. So, and here of course you can analyze high order modes, and this would be, for example, a monopole high order mode, which you cannot use for acceleration, because as you can see here, the directions of the electric field are opposite. So if an electron comes this way, for example, it will see field stopping him until it reaches this point, and then it gets accelerated, for example. And of course you can plot the magnetic field for this one, and so on and so on. In this case we can only see monopole modes because we are using boundary condition specific for this case. But after you do this, you can compute for the full cell just by doing revolution of this system, analyzing this again, and this will give you, of course, all the modes present in the structure to the compute frequencies. So once you get the correct results for this, you just have to take this cell, supposing it's the right model, you just have to take this cell and then start doing the full design. So then you will first do what the cavity is. So you will replicate the cell as many times as many cells you want to have in your structure, and then another important thing is that you have to obtain a field flatness behavior. That means that the field has to be constant in all the cells through the cavity, and for that you just have to do fine-tuning of the first and last cell. In order to get that, you just have to modify this radius here and this radius here in order to get the proper values, and also taking care that your electric and magnetic fields don't get changed so much. And then, as I said before, you just define the waveguide dampers, you define the beam pipes, and you put an input coupler, and then you wait and see that your cavity performs as you were expecting.